So it's a little bit dark anyway here. And okay, so now we do a final lightening up of the audience with lightening up of the slides. Thank you so much for inviting me, and especially for the honor to be the final culmination point. And I really want to start with this big thank you. I mean, this was amazing. There are so many excellent, highly competitive projects over the last month. And it was a really great pleasure that we were and we are among them. And you see the lucky faces. So these are many of the winners. And from here to here is part of our Stanford Living Heart Project team. And then there are a few lucky Hyperion guys as well. Vaguely, but I mean, yeah, I think you get it. And in fact, for that specific project, we got another few awards. And so we are now working on something else, which is the living brain. But this is maybe for next time. No, just kidding. Okay, so allow me please only one slide about UberCloud itself. So we started as a community effort because we found out in 2012 that there was no acceptance in the HPC community about cloud. And it was even worse. There were so many hurdles, which you could read everywhere in the press, that I have to get down, sorry. That everybody was really deeply reluctant. And we decided to not immediately build a company. We didn't have that idea. We just wanted to know what the community really was thinking. I mean, you know, the engineering, the science community about HPC in the cloud. And the best way was, obviously, and is always, to work with the community together. So we built teams with mentors on our side. So we had a few colleagues joining. Everything was free. So everybody donated resources, expertise, time to these projects. In the meantime, we just finished project number 201, and we published almost 100 case studies. We did about 300 publications in, insideHPC, HPC Wire, and a ton of others, especially engineering ones. So just let me run quickly through that. Very early, we discovered containers. At that time, Docker released their very first version in San Francisco, and we were part of the workshop, the first workshop, and we decided, that's it. We turn microservices containers into macroservices containers by adding about 30 plus HPC layers to it, like MPI, InfiniBand, GPGPU, and many more. So we have a white paper, so if you're interested in that, it describes the whole thing. One of the specific projects was with Intel and Lawrence Livermore National Lab support. We were able to turn this single-node, single-container environment in a multi-node, multi-container environment. And we were able to prove that it scales in the same way as bare metal is scaling. Right? So then we turned everything into real CAE, computer-aided engineering, software containers, later life science, oil and gas, and so on. And finally, based on, especially here, Intel and HPE's support of the whole thing with their hybrid HPC infrastructure, which we are now, with our containers, part of it, it culminated into this project number 197, which took us over a year because of many trials and errors, also on the living heart model side. The living heart was still developing while we were doing already simulations on the Advania cloud infrastructure. Okay, and I mean, very high level lessons learned, and in the meantime, everybody knows it, and colleagues here have nicely discussed it and talked about it. So obviously, we had to cope for many years with the security concern. But in the meantime, as we all know, I mean, clouds like Microsoft Azure, Google, Amazon, they are like Fort Knox, I always say. They are very secure, very professionally secure data centers. And now, in addition, we put another secure container on top of it for all the software and the data. I mean, this is a real nice, secure environment. So we were able to resolve this. Performance-wise, we were able to demonstrate that bare metal performance, right, with that one. Software licensing is still an issue for those ISVs who are not yet in the cloud boat, so to speak, to turn them into their annual perpetual software licensing business into a mixed, adding on-demand software licenses, on-demand or per hour, at least a much shorter term. And finally, the usability. This is very important for engineers. An engineer doesn't have time, 7 projects here, 5 projects here, to learn a new platform. But many of the cloud platforms today out there, this is platform X, platform Y, platform Z, etc. A company with 25 different softwares. They have to learn 25 different platforms. So they didn't want that. So here, a container, as you know, is packageable, portable, quasi-standard. So you can move a container back and forth to different clouds, including your own on-premise environment. So nothing to change. You package it once, it runs everywhere. So that's the usability, and I will show you, enabled by these containers. So this is one look and feel. As a user, when you go to Azure and you click on Ansys, for example, you get a welcome email with login and password. You copy-paste password, you log in, and you are immediately in that environment. And when users say, I want a demo, at conferences or so. So we say, okay, you can have a demo, you can have a live demo. And then the user is looking at that one, and usually they are very disappointed. So nothing sexy, as we tend to say, right? It is just your boring, familiar, traditional desktop look and feel. And that's exactly what the engineers were asking for when we started our UberCloud experiments. So you see the usual things. Yeah? You see your computer, you see all the different application icons, you see the trash, the terminal, etc. And now when you click, for example, on this Workbench and select like mechanical, let's do that, you see that. You see things which are used to use for the last 10 years already. Yeah? So immediately and without any change. So that's the beauty of it. So usability is something which we were able to take from your desk into the cloud. So this is a part of the Intel Lawrence Livermore project which we did together in 2014-15 timeframe. When Intel came out with support for the OpenHPC initiative then. So what we did is we took all the then 60 different tools, packages, etc., put it into one container and ran this container for an application which is called OpenFoam CFD open source. And you see, it is basically 2-3%. In some applications, you see vice versa. So there, in a certain containers are faster. So it is always kind of head-to-head. There is so far no performance loss to be recognized. So that's the architecture. I skip over that. You will certainly get the slides. Yeah. So it is a standard distributed architecture, and we have built together with HPE then later a hybrid HPC stack on top of that, which is continuously being improved now. So this is an Azure snapshot. No, I'm so sorry. This is not an Azure snapshot. This is an HPE snapshot. We have two large partners, so sometimes I tend to mix them. They don't really argue with that because they seem to respect each other, to say the least. So they partner in different, very large projects. And usually Intel is joining very often. And the nice thing is we have the great luck to work together with the three of them. So this is a standard architecture. So let's see. So this is a public cloud, private cloud, legacy. I mean your on-premise cluster, for example. Then you have different tools, orchestrator tools, automation tools, and so that was the very early phase of what we call the hybrid HPC 0.0 basically implementation, which we demonstrated last year at the ISC. Later on, the 1.0 we demonstrated at the SC in Denver. And let me go to the next one then. HPE added a few additional HPC automation lifecycle management. The CMU is the cluster management unit, which they enhanced with additional plugins. And one of them is then here the container. So this is now fully integrated. And a prototype is now running on Advania. And we take it from Advania just these days to prepare demos for the ISC onto other cloud service providers. So it's now one package, portable, and you throw it onto different Linux environments. Right. So that's where we are in the infrastructure, respectively. I mean, we are now moving more towards platform as a service layer here. And yes. So yeah, especially the security layers, because we always get this as question number one. Right? But again, the beauty with these containers and the difference to Singularity, for example, where Singularity is really a multi-tenant, multi-user container, HPC container environment. This one is single user as one of the components. Okay, it also runs on top of like CycleCloud, which has been acquired by Microsoft last September. It also runs on top of Univac Grid Engine as the scheduler in-house. And if you want to burst, you use UniCloud from Univac Grid Engine, and you have a complete hybrid HPC environment with existing tools. So we don't have to do a lot of development. We just do integration, right, these days, which is very nice. So the key is really that these containers are running on a dedicated server or many servers. There is no multi-tenancy, which means we know that Docker allows root access, which is dangerous in a multi-tenant environment, but this is single tenant, right? So therefore, the user gets 8 servers, 8 containers, ANSYS Fluent, whatever, and there is no interference and no potential interference with anybody else in that big data center. And then there's the standard stuff, the security layers, network storage, PKI of the firewalls, and HTTPS or even VPN access. Okay, so very quickly, I know we don't have a lot of time, but we will make it. So there is now this amazing case study, which I mean, we owe a big hug, or we want to give a big hug to especially this company here. So this is Dassault Simulia. Steve Levine, who is from Dassault, he's leading the Living Heart project. We just had a member meeting in Paris at Dassault's headquarters in Vélizy, and there were 150 members now. So it is, in the meantime, a huge project. In 2014, they got funding from FDA to do something like that. There was just Abacus. And they enhanced Abacus successively to include multi-physics with electro and other things which you need for the heart, for example. And then regularly give it to the community. And the community is currently playing with it. This is the first real big project which is commercial ready, so to speak, right? And we will, and as you see, so it is studying a real hard problem and a very important problem. As you know, arrhythmia is basically the warning first signs of a heart attack, very often. And many arrhythmias, respectively heart attacks then, are lethal, unfortunately. And there are millions of people worldwide every year which are affected by that. So, yes, so it is about drugs. And there are some drugs which are known that they cause arrhythmia even. Yeah? So the doctor should know. And this moves towards personalized medicine. Right? So you have a lot of good information about the patient. I will get back to that. And then you have the different drugs which you can simulate then against it with HPC. And we'll get to that. And okay, so this is some very quick statistics. So atrial fibrillation or fibrillation affects 2% of the whole population. Right? This results in that many deaths, etc. So sudden cardiac death is the cause of about half of the deaths due to cardiovascular disease, or about 15% of all deaths globally. So it's an issue, obviously, right? About 80% of sudden cardiac death is the result of ventricular arrhythmias. So that is important to basically prevent. And that was the aim of this project. Okay, so the project itself, it has the members are mainly leading cardiovascular researchers, educators, medical device developers like stents, for example, valves, and also the material behaviors of them, because once implanted, ideally they stay for a few years, right, safely. And regulatory agencies and practical cardiologists. So the shared mission: develop and validate highly accurate, personalized digital human heart models. That's the whole big project. So that is, models serve as a common technology base for education, training, device design, testing, clinical diagnosis, etc. Right? Rapidly translating current and future cutting-edge innovation directly into improved personal patient care. So the environment. It is. So we did this together with Advania. So Advania donated the resources for that, and HPE sponsored it. And it was basically the HPC as a service infrastructure, built upon 100 HPE Pro Reliant servers, like 3,000 cores. We didn't use all of them because there was production environment parallel to that. So real commercial users and very modern hardware at the time when we started. That was 1.5 years ago. And our software containers, they hosted the overall living heart software, Abacus software stack. Tested, etc., and fluid structure, electrophysiological modeling. So that has been developed by Stanford, by Ellen Kuhl's department into the whole model. Okay, so what we found out is, there was about half a year trial and error, right? So which we didn't really count, so that we found out that the LHP model scaled well up to 240 compute cores, linearly basically, and then the scalability started to flatten. Right? So we decided that, and that was hundreds and hundreds of compute hours on single node to about 10 node, where we looked at the scaling for the final 42 simulations, each of them about 40 hours on 5 nodes. So that's what we finally selected. And the study was about identifying drugs causing arrhythmias. So 42 drugs where, the experiments, there were a ton of information about experiments with animals and with real humans, and where the researchers know exactly what happened in certain circumstances. applying drugs by blocking different, and this is something specialists understand, ionic currents in cellular model, replicating what has been observed before in cellular experiments. Okay, so they had experiments to compare with, which is always nice. And for each case, we let the heart beat naturally and see if the arrhythmia is developing. So this is one of the results. As you see, what you see here is the electrical activity during one beat, right, from left to right. And this is top is the healthy heart, and the bottom is arrhythmia, obviously, more chaotic behavior. And let me just see. Yes, comparing the electrocardiogram, this is a specific drug here, which is sotalol. And cardiologists say, oh, no. So what you see here is really how arrhythmia develops. And this is, I should show that. This is really the simulation results. And so this is not the original electrocardiogram measured, but it is the one calculated. So Stanford found out that the simulation results are nicely coinciding with the experimental results. So then there is two nice videos. Let's start with the one on the left-hand side, which is the healthy heart. And that's another drug, quinine. And let me see. So these are five beats. And you see, you recognize very regular pattern of this electrical behavior. So that's 5 times. Okay. Sure, thank you very much. Okay, and then this is quinine, and it's that. So try to find some regular behavior. There's no chance, right? And this is amazing. So you can really now, depending on the patient herself, exclude medicine, which is potentially causing arrhythmia there. Okay, so we are almost done. Oh, okay. Let me see. So it's, okay, so one moment. Okay, let's get back. So the takeaways are, okay, so these are the partners who have contributed it. So Stanford did all the scientific work behind it. In the meantime, they presented it at different cardiology congresses. So they call it a breakthrough, which is nice. Simuli as a software, Advani as a hardware, and HPE and Intel supported this with very good funding, and everything hosted in our UberCloud software containers. That's what it says here. And with that, yes, I would like to thank you very much.
So Wolfgang, I want to mention something about our award program. Many of the judges are in the crowd here, the steering committee. And one of the most difficulty we've had, because we've actually only given them out to less than 1/10 of the people who apply for the award, is what the award centers on is not the computer. Mm-hmm. It's not the software in the computer, it's what's the outcome. How is it used to make some money, help society, help the world? And your example is absolutely a perfect fit for that. And so we appreciate you making the submission.
Yeah, same here. Appreciate your support.
And we ask everyone in the audience too, if you have examples, and what the award is based on is the outcome. So we want something that has a positive outcome. Please submit an application for the award.
So I have a question. Maybe this has to go to medical experts, but so how do you calculate the effect of the chemical goes through the digestive system, gets absorbed in the bloodstream, and then it's affecting the electrical currents in the heart? How is that calculated?
Yeah, okay, so I'm sure all of what you mentioned before that is not included, but it comes into the system. I mean, obviously the nonlinear partial differential equation system, etc., as initial and boundary conditions. Right? So the initial condition is basically the scan of the CT. Right? So there is a patient specific CT which gets included as the initial condition. Also the geometry of the heart. Everything is very patient specific. And then in this case, two things are simulated. It is basically with abacus. So it is the structure, the structural change under the influence of the electrical impulses, which go through what they call Purkinje network. So this is something for the inside. I have no clue how that works. It's very highly complex. Scientists have discovered a few decades ago that the inner part of the heart is covered with a very fine network which transports these electrical impulses, the regular ones, and which are the ones which make the heart really pump, right? Contract, detract, contract, etc. And then that causes the blood to kind of flow through your body. Everything else I cannot answer. Sorry.
Great. Thank you.
Okay, thank you so much. Yeah, great pleasure.